All right, welcome to the quantum chemistry note package. I want to start with electrons. What are electrons? Well, as it turns out, electrons behave as both particles and waves, both as particles and waves. Like particles, they have mass, they have position, but like waves, they have energy. So the energy associated with these waves exists in packets called quanta. And these packets emit light energy in the form of photons. So let's take a look at some parts of the wave then. Let's take a look at some parts of the wave. So here's a typical wave, right? Up and down. So what are the parts? Well, the top of any wave we call the crest of the wave. The bottom of the wave we call the trough of the wave. So this is a trough, this is a trough, this is a trough. The distance from the middle to the top or the middle to the bottom is called the amplitude. There's no name for the bottom to the top, but middle to top or middle to bottom we call the amplitude. Remember, there's no name for bottom all the way to the top, right? Wavelength we've described as the distance from the top or the crest of one wave to the crest of a different wave or the next wave. We could have easily done it from the trough of one wave to the trough of the next, or in fact any point to any corresponding point we call the wavelength, and the unit for that, or the symbol for that, is this lambda symbol here, lambda. Now waves come in all different sizes and have different energies associated with them. So for example, this wave that I'm showing here is a low frequency wave. That means it doesn't move up and down very fast, as opposed to this wave here that's a high frequency wave. This wave here is going up and down many times per second. So this is a low frequency wave, this is a high frequency wave. Low frequency waves don't go up and down very fast. High frequency waves go up and down very quickly. So if a wave is low frequency, it's also low energy. If a wave is low frequency, it has a low energy. If it's high frequency, it has a high energy. So for an example of a low frequency wave, we can take radio waves. Radio waves are low frequency. Gamma rays, on the other hand, are high frequency waves. Gamma rays are high frequency rays. Okay, the distance from the crest to the crest, or the trough to the trough, we've already said, is known as the wavelength, and it's usually measured in meters. The number of times a wave passes a fixed point is called the frequency, and it's measured in waves per second or hertz. Okay? Now, for all electromagnetic radiation, there is an inverse relationship or an inverse proportion between wavelength and frequency. There's an inverse relationship between wavelength and frequency. And the greater the wavelength, the less the frequency, and vice versa. The greater the wavelength, the greater the wavelength, the less the frequency, and vice versa. We'll see later on that that's because of a equation that's written as this: speed of light is equal to the wavelength times the frequency. The speed of light is equal to the wavelength times the frequency. So if this is a constant, that means if one goes up, the other has to go down, and we call that an inverse relationship. Now let's talk a little bit about the electromagnetic spectrum. The electromagnetic spectrum is the spectrum of all waves that exist, from high frequency waves to low frequency waves. Now high frequency again means it goes up and down many times, like gamma rays or high energy waves. Low frequency or low energy waves, like radio waves, are much larger, but they're also much slower. They don't have the high frequency that a high energy wave like gamma rays do. An example would be radio waves. Now, right about in the middle is the visible light spectrum. This is the spectrum, the part of the electromagnetic spectrum that we can see as humans. These are visible to our eyes. This part of the spectrum is visible to us. It's called the visible light spectrum, and it's right in the middle. And we'll talk a little bit more about the visible spectrum in just a moment. Okay? All right. So gamma rays then have a very small wavelength. Gamma rays have a very small wavelength. Thus, they have a very high frequency. Remember that inverse relationship. If one's high, the other one's low, and if one's low, the other one's high. These rays are very high in energy and can cause damage to our DNA. Radio waves have an extremely long wavelength, so they have a very small frequency. They have a long wavelength, so small frequency. Remember that inverse relationship that we talked about. Now the speed of light is equal to the wavelength of a wave, that's written as lambda, times the frequency for all electromagnetic radiation. The speed of light is equal to the wavelength times the frequency for all electromagnetic radiation. And again, here's the formula that we use. Speed of light is equal to wavelength times frequency. Now, use a triangle. C on top, lambda here, that's wavelength, frequency here. If you want to know the wavelength, cover up the wavelength. Wavelength is equal to speed of light divided by frequency. If you want to know frequency, cover up frequency. Frequency is equal to speed of light divided by wavelength. Now, what is the speed of light? Well, C is the speed of light, and it is 3.0 times 10 to the 8th meters per second. So now we can clearly see why wavelength and frequency are inversely related. They're inversely related. When wavelength is large, the frequency is small, and vice versa. When one is big, the other one's small. Okay? Now, Max Planck said that energy existed in packets called quanta. Energy existed in packets called quanta. And that if you knew the frequency of electromagnetic radiation, you could calculate the energy that it possessed using this formula. Energy is equal to Planck's constant times the frequency. Energy is equal to Planck's constant times the frequency. Again, we can make a triangle. Energy on top, Planck's constant here, frequency right there. If you want to know frequency, cover up frequency with your finger. Frequency is equal to energy divided by Planck's constant, and you've got it. Okay? So there's the triangle. Where energy is in joules, Planck's constant is 6.626 times 10 to the minus 34 joule seconds. And that is joule seconds, by the way, not joules per second. That's joule seconds. 6.626 times 10 to the minus 34 joule seconds. And frequency is measured in hertz. Okay, frequency is measured in hertz. So energy in joules, Planck's constant, 6.626 times 10 to the minus 34 joule seconds, frequency in hertz. In other words, if a wave has a high frequency, such as gamma waves, then it will have a high energy. If a wave has a high frequency, such as gamma waves, then it will have a high frequency. So now let's apply this to the visible part of the light spectrum. Now remember, the visible part of the light spectrum can be written as Roy G. Biv. Those are the colors that we can see, Roy G. Biv. Remember also that R, the red, is on the low end of the energy scale. Red is, just remember, red is low energy, violet high energy. So in this direction are the radio waves. Radio waves are very large and low energy, and in this direction are things like X-rays and gamma rays, very high energy waves. Now, a photon of red light is lower energy, has a lower energy than a photon of green light. Why? Well, red is positioned lower than green. A photon of violet light has a greater energy. Violet's way up here on the scale. Violet's here, as compared to yellow, which is right there. A photon of orange light has a lower energy. A photon of orange light has a lower energy, here's orange, than does indigo. Here's indigo. So orange is closer to the red than is indigo, so it's a lower energy, and we say that a photon of orange light has a lower energy than a photon of indigo light. Okay? Good. All right. Electrons on the lowest energy levels. Electrons on the lowest energy levels of an atom are said to be in the ground state. The lowest energy levels are said to be in the ground state. If the atom encounters energy, such as a gamma ray from the sun, or maybe heat from the flame of a Bunsen burner, the electron may absorb energy to move up to a higher energy level. The electron is said to be in the excited state when that happens, But it cannot remain there forever, so eventually it emits energy in the form of a photon and falls back down to ground state. So how does that work? Okay, so here we have the nucleus of an atom. This is n equal 1, n equal 2, n equal 3, n equal 4, and it goes on from there. When the atom is hit by electromagnetic radiation, what happens is it moves up. Some energy source moves that electron up higher and higher and higher, but it can't, and it absorbs energy as it moves up. So with each step up, it's absorbing more and more energy, but eventually it has to fall back down. And as it falls back down, it's going to emit energy in the form of a photon, So again, as the electron is moving from lower to higher energy levels because it's absorbing energy, eventually it has to fall back down, and when it does, it's going to emit energy in the form of a photon. When electrons fall from higher to lower energy levels, they release energy as photons to form a bright light spectrum, which scientists can see. So this is an example of what a bright light spectrum may look like. This may be a bright light spectrum, for example, for hydrogen. Notice the discrete lines, one here, one here, one here, but nothing in between. That happens because electrons fall from specific energy levels, not from anywhere, but from specific energy levels. And that's it. That's the first part of quantum chemistry. I'll see you on the next part. Thank you.